So, a little insider information here. I don't know if you've ever recorded a video with PowerPoint before, but you can record your voice over the slides in any order that you want. So while this is the beginning for you, it's actually the last thing I'm recording before I save the video and post it to YouTube. And I'm realizing as I'm going through all this that it's probably going to be a little weird sounding because not only am I all stuffed up and congested, but I'm also recording it in a mostly empty basement, so it's likely there's some weird echoes going on right now, and hopefully this all makes sense. Anyway, when I was your age, I had an English teacher who is still my favorite teacher ever. And this guy had a very distinct voice. He was very formal and articulate, and if he wanted, he could have made relaxing videos on YouTube to help people fall asleep. But I remember him sometimes starting off class by saying things like, "Good morning, beloved students." And I'm not willing to go that far. Maybe we get to know each other a little bit better first. Why rush things, you know? But anyway, I hope everyone is doing well as can be expected at this really strange time. I've been ending videos like this, but get out there right up front this time. Please reach out to your classmates, teachers, counselors, administration, anybody. If there's anything we might be able to do for you, I don't know what we can do for each other, but we have to try to be there as much as we can be. So let's begin. And I'm actually adding this slide as the final thing I do because I realized when we get back to school, ask me to tell you about my teacher a little bit more because I've got a great story about him reading To Kill a Mockingbird when I was a sophomore in high school. And it's probably something you won't care about, but at least amuse me a little bit. So when we see each other again, remind me to tell you that story. And with that extended intro, happy Tuesday, Limerick Science students. I had a student once ask me if this picture was really how dinosaurs happened or however they worded it, and unfortunately it's not that we know of. Anyway, how do we get energy? You know this. Maybe something like that. Does that sound familiar, possibly? So that answers that question, but where did the energy in food originally come from? Think back to earlier in the year, and where does all energy on Earth originally come from? Where do we get energy? Maybe not us directly, but someone gets the energy, and then they use it to do stuff, and we are happy that they are able to do that stuff, and eventually the energy gets passed to our food. But that's what we're going to go back to today and see how this all works. Today we're talking about how nutrients are recycled. So living things need certain materials to survive, nutrients like we get from food. And this goes back to the circle of life idea that I sang about in the video a few days ago. Animals eat, and when they go to the bathroom or eventually die, the molecules of their bodies then go back into the ground to become new plants and keep the whole cycle going. This is just like taking paper, plastic, and recycling it in bins, reusing things to make good use of resources around us. There are more organisms involved in this than just animals eating and dying. So first we have scavengers, or detrivores. And these are things like these buzzards in the picture. They feed on scraps of food left behind by other larger predators, and in doing so, they break it down, the animal remains into smaller pieces so that it decays and rots a lot quicker. So the environment gets it fast. It doesn't have to wait for the big chunks to break it down, like if we just put food directly into our stomachs, or we then chew the food into smaller pieces. This is the same kind of thing. It's mechanical digestion, just like what happens in our mouths. And we call this rotting material of plants and animals that they break down stuff into detritus or detritus, however you want to pronounce that. Now at this point, things called decomposers are able to fully break it down, whatever's left over, and put the nutrients back into the soil. This is like the chemical digestion that happens in our stomachs and intestines, and this is done by things like fungus, mold, stuff we typically think are kind of gross, but they play an important role in the environment to actually return all these smaller, break it down nutrients back into the ground so they can be absorbed by plants, absorbed by animals, whatever's going to happen with them. That's all we're actually going to worry about, living material. We don't need to talk about animals or stuff any more than that. And instead, we're going to turn our attention to important compounds and elements needed by living things. So we're going to go back to some of the CHON elements and things like that from the beginning of the year. And first up, clearly, we're going to talk about water. So starting out with water on the ground in lakes and oceans at the bottom left there, what do we know tends to happen to this water? Why are there all those arrows going up into the air? So when liquid surface water absorbs enough energy and gets hot enough, it will evaporate into the air. And then once it's up there, these water droplets can condense together into the clouds that we see every day. Eventually, this water becomes too heavy and falls back down as precipitation like rain or snow. Now, when it hits the ground again, it eventually becomes surface runoff when it flows into a body of water, or it can be absorbed back into the earth and join up with the groundwater. So hopefully you remember something like this from earth science, but this is just the water cycle. Water gets hot, it goes into the air. It comes together when it cools down, it gets heavy, it falls back down to earth again, and the whole thing keeps working. So hopefully it sounds familiar, and if it does, we can move on. So a very similar kind of thing happens with carbon atoms that make up organic compounds in living things. Let's start at the top left again. At this point right there, carbon atoms form the fossil fuels that we burn for energy. So coal, oil, natural gas, those are all just big chains of carbons and hydrogens, but it's mostly carbon. So this puts carbon dioxide and other compounds of carbon back into the atmosphere in the air. Even if there's no industrial processes involved, where does carbon still come from? How does carbon get back into the air? As this picture reminds us here, we release it every time we breathe out. Anytime any kind of organism that carries out cellular respiration does that, anytime they exhale, we will release carbon dioxide back into the air, and that returns it to the environment in a very, very important step. So where does this carbon dioxide go then? You can either follow the picture, which the arrow is only going one place right here, or hopefully remember from earlier in the year, eventually it should get absorbed by plants again and used for photosynthesis. They make their own sugars. This incorporates the carbon dioxide, takes the carbon atoms and puts it into the sugar molecules. That's C6H12O6. That C is carbon. There's carbon now in the plant. The plant has absorbed carbon out of the atmosphere. Carbon, oxygen, it takes in water, so it's hydrogen, oxygen, those Chan elements again, and makes its own pieces, makes its own food, makes its own parts. When animals eat the plants, these carbon atoms now become the molecules of the animals' bodies. And then when they die, it returns to the ground where it gets absorbed by the plants again, or turns into fossil fuels if enough time passes. So again, we saw that word detritus before, detritus. That's the same thing over and over again. All these materials that the animals eat eventually has to go somewhere. It's that food chain, the food web. So if the rabbit eats a plant and then gets eaten by the lynx, those molecules are being passed on. And once that thing dies, or either of them dies, it goes into the ground and becomes the detritus. It becomes those minerals and those materials that can now get absorbed by the plants again, or again, if enough time passes, it could actually become the fossil fuels that will not be used by people in the future at this point, because the planet won't be around, or we won't be using fossil fuels at that point, hopefully, but it could turn into that kind of material. Okay, so here's the deal with nitrogen. We talk about water cycle, we should do carbon cycle. Nitrogen is a really important element, as we learned at the beginning of the year. It's one of those Chan elements, CHON. It's in proteins and nucleic acids, our DNA, so it is really important, but we're not going to go into crazy detail here just because you don't need to know a lot of it. So basically the nitrogen cycle works a lot like the carbon cycle, in that things are in the air, they go into plants, they go into animals, everything kind of loops around again. Most of the atmosphere and the air around us is nitrogen gas, but this nitrogen gas doesn't get absorbed for photosynthesis the way carbon dioxide does. That's the only gas that plants need for that. So instead, some plants have these little bumpy things on their roots called nodules. And it is a science technical term, these little bumpy things. Look it up. But that's what it is. So bean plants and peas and things like that, they have these little kind of bump growths on them. Those are called nodules. And they're on the roots. Now, inside of these nodules are a special type of bacteria that actually pulls the nitrogen gas out of the air and turns it into a form of nitrogen that the plants can use. So if you've ever heard this word, these words nitrates or nitrites, ammonium and ammonia, those are all chemicals that have nitrogen in them. And the bacteria in these nodules right here in the roots of some plants, not all plants, but some plants, help to take that nitrogen gas out of the air and turn it into these materials down here, these compounds. Now, once those compounds are in the soil, there are also compounds that are in a lot of fertilizers and things like that. The plants can actually suck them up and use them. That's why we use fertilizers. It's got a lot of these chemicals in them that the plant needs that it can't just normally get out of the air. So we artificially put it into the ground sometimes as fertilizers. Otherwise, you'll see sometimes farmers planting things like bean plants and pea plants, even if they're not growing those as a crop, just because it will help their other plants grow. So let me see where I went here. My notes, I lost this here. Yeah, so it absorbs nitrogen gas out of the air and turns into things the plant can actually use. And the rest of this we really don't have to worry about. I don't want you to worry about these things, assimilation, denitrifying things. Those are words we don't need to know. The gist of this is just, again, that plants pull nitrogen gas out of the air, some plants, so they can return to the soil, much like other plants or all plants would do with carbon dioxide in the air in the carbon cycle. And we're going to skip all this too, because these are fairly unimportant details right now. All this page right here says is what we just saw. Bacteria turn nitrogen gas into some kinds of compounds, and they turn them into other things, switching back and forth a little bit. Sometimes other bacteria turn them back into nitrogen gas to go back into the atmosphere, but for the most part, they get absorbed by plants, and it really doesn't matter. So if I left this in your notes, you can go ahead and cross it off right now. I don't remember if I left it there when I gave you the file, but we don't need to talk about it. We don't need to go over it. We're done. On that note, do go and fill in the form for today right now while it's fresh in your mind. And I believe I left 2 pictures for you in your content library originally for you to label the water cycle and the carbon cycle, not nitrogen, but I'm going to cancel that. So if you saved all the files that have been posted already, just ignore the nutrient cycle work from Tuesday. I'm not even going to check it. Do the form because I'm using those as if they were attendance. But instead of the worksheet that I have you do today, just take a few minutes and go work on any labs that you're missing. I know I've had a lot of people send me stuff, but there's also a ton of you who are still missing at least 1 or 2. So just try to make sure you get those done. You've, again, still got a couple of days. I know a lot of you are emailing me over the weekend that we're having tablet issues and getting to things now. That's fine. Take your time, but try to make sure you get those things done as best you can. And if you don't have any labs to finish, please try to find any amount of time today as best as you're able to just do something to keep yourself grounded. I don't know what anyone might be going through at home right now, but if you can just clear your head, take a few deep breaths, do something normal and regular for your life, whatever that may be, do it. It's really important. I'd rather have you do that than write the words evaporation and condensation into a 7th grade worksheet. So I said I had a few emails yesterday asking questions about work or labs, and that's good. Anything you need, let me know. I've been pretty responsive during the day. So if you need help, I'll try to walk you through any issues. I wrote a couple of longer emails detailing how to do worksheets and things like that, and that was fine. I put a lot of grades in yesterday. It's good to see most people keeping up with everything. Hopefully some kind of school normalcy is keeping everything as grounded as we can hope at this point. I know I said this yesterday, but check in with each other, make sure your classmates are okay, and we're here to help if you need anything, hopefully as best we're able to too. So on that note, stay safe and healthy. I'll talk to everybody tomorrow.